All right, so we're very happy to have Simeon Hellerman visiting from IPMU, and he will tell us about the B model and the Ginib model. Is that the
I
pronounce
don't
it?
know how it's pronounced.
Okay. Something along those lines.
Yes,
Take it away.
thank you. Thank you very much, Ted, and the organizers of this thingy, the TEP.
Theory of elementary
Particles, okay. Seminar. And yes, so I should say that today I'm going to tell you about some somewhat crackpot things, but not completely crackpot. So
We're recording, right?
We are.
well, I should say
With
only my contributions, which are crackpot, the contributions of my open collaborators who will admit to collaborating on this, they are not crackpot at all. And then I have names and sizes indicating how willing they are to have their names put on this. And there are a lot of other people who contributed too who don't want their names listed. Okay, but it's not that crackpot. It has some truth to it, probably. Just depends what your standards are. Anyway, thank you, organizers, for letting me talk about this. But today I'm going to be talking about some things. About quantum gravity. UCLA has long had a distinguished quantum gravity group, I would say. So today I'm going to be telling you about a fundamental connection between machine learning on the one hand and quantum gravity. You see the cursor? Oh, nice. You see the cursor? Okay. On the other hand, now that may shock you, may surprise, horrify, scandalize some of you. You're all keeping very poker faces. None of you has gotten up and walked out yet. It's only the first slide. Specifically, a connection between machine learning on the one hand and the only consistent theory of quantum gravity on the other hand, namely string theory. The great majority of researchers on machine learning and math physics study applications of machine learning to mathematics and physics. This is a large enterprise that has already generated many interesting results, blah, 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 including in cosmology, but also for fundamental theory, including string theory and even pure mathematics. And now there's a big Simon's collaboration that got funded just recently, which I think they call themselves the physics of learning, but in point of fact, that as far as we can tell, it's completely comprised of applications of machine learning to mathematics and physics. So the overwhelming majority of research on those connections, including what is being done by these, I guess so far seems kind of inaccurately named Simon's collaboration for the physics of learning, is the very, very different from what I'll be talking about, but I think this is a sort of interesting thing. There's a much smaller, still inchoate enterprise involved in the reverse direction, using ideas from theoretical physics to learn about machine learning, particularly why deep networks are successful in solving practical problems when they're successful, and also focused on expanding their domain of utility and improving their performance where they are already known to work somewhat well. So the subject already exists. We didn't invent it. There's some very beautiful extant work in the subject. So the current state of the art is well represented by a pedagogical reference from a few years ago by Dan Roberts and Shoyeda, also Boris Hanyan, which represents many of the most important ideas in the quantitative analysis of machine learning in large networks, using ideas that are familiar to theoretical physicists, particularly ideas from quantum field theory. Okay. But I say ideas from quantum field theory rather than a systematic application of quantum field theory. And the first part of this talk is trying to explain why. So in this sort of Roberts-Gaeta paradigm, they define something called the representation group, quote unquote, which describes how information propagates from one layer to the other of a deep network, in analogy with Ken Wilson's formulation of the renormalization group, which describes how couplings evolve from scale to scale in quantum field theory. So I'm not going to describe this Roberts-Gaeta framework here, but I encourage all quantum field theorists, all theoretical physicists to read it. It was very useful to us, understanding what goes on in this deep learning stuff. So I'm choosing my words carefully here. This Roberts-Gaeta framework does not actually use quantum field theory except as an illustrative analogy, but it's only an analogy. So as a theoretical physicist, I learned a great deal from it, but I want to emphasize it's only an analogy that stimulates certain intuitions in the minds of a physicist. The analogy breaks down in certain important ways, and since I'm not going to explain these kind of pseudo-RG ideas, let me just give you some sketch of it, why the analogy is useful, why the RG in the standard sense is not really applicable, and finally, what should replace it if one wants to find a theoretical tool that is directly applicable in any kind of a precise sense. So why is the analogy useful? The analogy is useful due to the largeness of the large network, okay? All the stuff I'll be talking about is applicable to large networks, not small ones. The size is important. The width of each of the so-called hidden layers, and also for those of you not who aren't deeply immersed in this subject, which you probably shouldn't be, by the hidden layers. So what deep networks do is to take a bunch of data and to map that data actually into a space much bigger than itself, and then to process and the size of the bigger space, the bigger space is called the hidden layer, and or there's a number of hidden layers usually, and the network propagates the information from each layer to the next via some sort of a randomly chosen formula, which is then successively improved by what's called training. So one can think of something like gradient descent, trying to minimize the difference between the outputs versus the expected outputs for some set of training data. But when people talk about large networks, they mean the case where the so-called hidden layers of the space in which the larger space in which the data gets mapped into is parametrically large. So when the number of degrees of freedom, which is to say the width of the hidden layer, is large, the renormalization group is by far the best developed tool for dealing with any kind of quantum or statistical randomness for interacting systems in the limit of a large number of degrees of freedom. But that said, the renormalization group, in the sense that we are used to studying it, let's say, maybe what I'll be talking about is a more general renormalization group, but the renormalization group, as we are used to studying it, is not a universally applicable tool. RG techniques, in the usual sense, rely on a condition of locality. So there has to be some kind of pre-existing notion of proximity, spatial proximity, and the RG describes the evolution of interactions as a function of scale, when those interactions are local in some approximation with respect to that prior notion of proximity, and that doesn't always exist. Sometimes it does. It's a very general notion, but there are things even more general than that. So But deep networks are similar to quantum field theories in that they do have a parametrically large number of degrees of freedom at each layer. They also have a sense of locality in the quote unquote time direction, where you can think of the label of the hidden layers as a kind of Euclidean time direction. There's a continuum limit in which the number of hidden layers is taken very large, and the sort of Euclidean time direction becomes continuous. And then we have a stochastic choice of maps between adjacent layers, which turns the construction of the network into a statistical system local in imaginary time, which you could Wick rotate and turn into a kind of quantum or quantum-like theory on analytic continuation to real time. So those are the ways in which deep networks are similar to quantum field theories, but they're also quite different from quantum field theories because they do not have any sense of proximity, so there's no sense of locality to the interactions among different degrees of freedom in a given layer. And in particular, there's no derivative expansion. So there's no a priori principle that makes some interactions more relevant than others when the network becomes large. There are principles, but there are no what you might call a priori principles, right? You can't just look at the system and kind of make an educated guess which interactions are more important than others, which you can do for local theories. So the result is that information spreads much more rapidly and promiscuously through the network as a function of layer time than is the case in any local quantum system. And so the conventional normalization group loses much of its utility. In some sense, a large network is the other extreme from a quantum field theory. Instead of propagating information only to infinitesimally close by sites, it propagates information arbitrarily strongly to all other sites. So when I discuss the limitations of the Roberts-Skaeta pseudo-RG framework, I'm comparing it to this very high standard of the field theoretic Wilsonian RG, where we have a well-defined hierarchy of relevance, a priori, a well-defined sum rules and unambiguous calculability of amplitudes, modular Wilson coefficients, quantitative theory of the evolution of those Wilson coefficients with respect to energy scale, an algorithmic framework for the computation of finite size corrections, a quantitative theory of critical phenomena and phase transitions, many other such things. So what we would like is to bring the theory of deep networks up to that standard, up to the standard of the Wilsonian RG. So we want to know what are the tools that we can use to bring the quantitative analysis of deep learning to that level. And so Roberts and Yeda and Hunyan, I think, got these ideas teed up, and ready to be dug into, but did not actually solve these issues. And so that's the target here. So the need for such a controlled description is acute. There's a somewhat well-developed theory of large networks, both at fixed depth and large width, in which they behave somewhat boringly. And then more recently, a double scaling limit where the width n and depth L are taken to infinity in fixed ratio, in which they behave much more usefully. So the recent deep learning revolution has exploited this limit. So when you use, ChatGPT or whatever, specialized networks to do mathematics or protein folding or amplitudes or whatever, you're using networks which are constructed in this sort of limit, which are both wide and deep, with the aspect ratio taken more or less fixed. And by the way, I should say that I'm going to be talking about the ideas that are relevant to this later limit of wide and deep networks. But then the actual example, which I'm going to be talking about today, is just a one-layer network. So L equals 1. So I'm not going to be able to tell you today about a quantitative attack on the interesting limit, but I'll just be telling you some general ideas for how to construct it, and then a simple case for a wide shallow network where we have an exact control description. Anyway, real networks are always finite sized, and generally finite width corrections are important. And additionally, the behavior of the double scaling limit raises some pressing questions. So at small double scaling parameter, the network tends to Gaussian behavior, or to be slightly more precise, what's called neural tangent kernel dominated behavior, which is not exactly the same thing as Gaussian, but let me leave that distinction aside. At large double scaling parameter Q, the network behaves chaotically with infinitesimally small changes in the inputs producing wildly different outputs. And as the size of the network becomes larger and larger, the crossover region in aspect ratio space becomes sharper and sharper, becoming an infinitely sharp phase transition as a function of the aspect ratio at infinite n. So this is something which is known empirically. This is not understood theoretically why this is the case. It's an important empirical fact. It's clearly a critical phenomenon of some sort, but it's only understood empirically. And the critical value of Q depends on lots of different things. Depends on the nature of the data, depends on the training algorithm, and it depends on the other features of the network architecture. So there's no, unfortunately, or fortunately, because it leaves us something important, interesting to do, there's no quantitative theory of this extremely important phenomenon in deep networks. So what's urgently needed is a principled framework playing the role of the field theoretic Simeon RG for computing. Oh, that should be spelled with an A. I'm so sorry about that. The optimal value, the critical value of the aspect ratio for a given network architecture and training algorithm, finite size corrections, the data dependence of all this stuff. So many things you'd like a principled framework to compute all these things ab initio. We don't have those.
Do you expect, even if you have such a theory, to be able to compute this critical Q?
Yeah.
It should be universal, you think?
No. As I said, it depends on a lot of these things. But given these inputs, yeah, it should be possible to compute. Yes.
But it sounds a bit like computing the critical temperature.
Okay, let's say no harder to compute. It should be no harder to compute than, for instance, the critical coupling in the Wilson-Fisher model. Let's say if we could get it to be that computable.
But that's pretty hard in field theory. That is not true.
Not really. I mean, it's hard if you don't know the answer, if you don't know how to do it. But once you have the right conceptual framework set up, it's actually very easy to do. Right? So what Wilson and Fisher and Kadanoff and those smart people did was to say, let's set up the conceptual framework that allows you to do that, and then they did it, and it was quite easy. So what we're going to do is to try to find the right conceptual framework in which to compute these things for all-to-all interactions, and they're so that's what we're trying to do here, and we think we have an answer to this question, and it's a very interesting answer. I hope it's something that you'll find as interesting as we did. So one clue comes from work by Maldacena, Schenker, and Stanford, following up on earlier work. So in this paper called A Bound on Chaos, the authors prove that even with arbitrary, maximally non-local interactions, there's a hard limit to how quickly information can be scrambled as it spreads through a quantum system, and the bound appears to be saturated by matrix quantum mechanics and other matrix-like systems such as gauge theory in the large N limit. So these considerations suggest that no matter how complicated the ensemble of stochastically constructed deep networks might be, the ensemble should be no more complicated than a matrix quantum mechanics. So let me make three key points here. So not only is the ensemble of stochastically initialized trained deep networks no more complicated than a matrix quantum mechanics, but I'm going to argue that it is a matrix quantum mechanics, literally a matrix quantum mechanics, or a not necessarily unitary matrix quantum mechanics. And that the matrix is just the so-called weight matrices of the deep network. The time direction is the layer index and so forth. So now the behavior of matrix quantum mechanics at large rank can be boundedly but extremely complex. And the complexity is maximized when the matrix quantum mechanics is maximally strongly coupled in a certain precise sense. So in the remainder of this talk, I'll flesh out as much detail as I can and explain many terminologies and assertions that I've left unexplained so far. And I haven't given this talk very many times, and it's a moving target because we keep learning more every time I give it. But so I've divided the explanation into small self-contained mini lectures that go roughly from most essential to least. So you'll get the important stuff if I run out of time. But the main takeaway, our conclusion, of which I hope to convince you to some extent today, is that the correct quantitative controlled description of deep learning is a string theory. And what I should say is that, I'm going to talk at the end about the simplest possible case, the so-called Rosenblatt perceptron, the one-layer network, just as a kind of proof of concept to show that, we have a recipe for working out what these string theories are. But that's not so important. What's important, what I rather focus on, is convincing you that string theory in general is the correct controlled quantitative description of large networks in general. So questions on the introduction? Yeah, Ryan.
Yeah, you said that there's this critical Q.
Yes.
It's like a critical phenomenon. What are some, and it's observed numerically. What are some of the observables that people look at?
Thank you. So the main thing people study, I should have, if I can dig around in it, but maybe I shouldn't do it in real time. I should dig around my notes. But there's this phenomenon called double descent. So the main observable that people care about is, how well does the network perform on the data you haven't trained it on? Right, so people take the data set, they divide it into training data and test data, and then they construct the network by choosing network parameters at random to begin with, what's called an initialization, and then they train it, so they deform the ensemble to make the so-called test loss lower and lower, meaning the difference between the outputs and the expected outputs, right? So the observable is what they call the training loss. They minimize the so-called training loss. They both begin with T, so I often say the wrong thing. You minimize the training loss and then observe the test loss. The test data is all the data which you can train on, and you want the test loss to also be as low as possible. You hope it will be as low as possible. That's the main thing people care about observing. But the actual behavior of the test loss displays this phenomenon called double descent, as you make the network, I can't really draw very well, but as you make the network bigger and bigger, so this is the test loss, meaning basically the log of the difference between the outputs and the expected outputs. This is the test loss. This is the size as measured by L or N or whatever, just the total number of degrees of freedom. And
fixed Q.
No. You can fix various things. Fix various things. But let's say you fix N and increase Q. Okay. But you can also this is a more general phenomenon. So you start out with, of course, a lot of test loss, and then as you make the network bigger, something happens which first sounds weird, but then you realize that it's sort of inevitable. You go to the over-parameterized regime, right? Where you basically, when the size of the network is roughly as big as the data itself, you get infinite loss because you're just fitting you're essentially just fitting every data point. So there's absolutely no reason for the next data point to be predicted in any way at all. But then, so that's kind of as expected. But then what was not expected and what led to the kind of deep learning revolution is that you then get better. You kind of monotonically better as you're extremely over parameterized. Now, of course, there are many right, since you're so over parameterized, you can fit all the test data. That tells you that the stochastic element at initialization is relevant, right, for the right part of the double descent curve. The stochastic element is extremely important. It sort of dominates what's going on out here, and it's for some mysterious, like the reason isn't understood, but it's empirically very clearly the reason why deep networks behave so well, because it's saying that in some sense a typical over-parameterized map, as chosen in some random way after training with a characteristic slice of data of kind of any structured data set, is very predictive. Who knows why? But seems to be the way things work. So that's the test loss is the thing that people look at. Where's my file?
And the singularity there is like a power law. Should I think of that as some critical explanation?
Good question. I don't know the answer to that. I should, but I don't. Yeah, good question. It may even depend on, again, like Ryan asked, what you're holding fixed, if you're holding Q fixed or N fixed or whatever.
But presumably as we vary Q, we get different plots that look like this, and then we should see near the critical point, like some scaling behavior.
That's right. Yeah. But I mean, the size is parameterized by L and N, so it should really be kind of a three-dimensional plot.
Yeah.
And that I think that singularity is always kind of where N squared L is the same as the number of parameters in your data, in your training set. I actually don't know that for a fact, but I expect that that's what's going on. I mean, the way it's been explained to me is that this singularity is exactly the point where you've just force fit every data point with your network.
That makes sense.
Is your goal to make a theory of the critical point or the decaying branch to the right?
The decaying branch to the right is where all the magic happens. Yeah. Although, I mean, but I should say that for large data sets, this is somewhere also in what you would call large networks. So, I mean, ideally, we would like to see this point in, even in shallow networks, right? It would be good. I mean, we're really aiming at a sort of a generic enough principled description of large networks that one could see this as well. But what people are actually interested in is this stuff over here. So that this is where the money is. This is some principled thing that smart intellectual people would want to understand. So I understand why you asked that.
I might want to think about that as like the UV somehow.
But that seems yes universal. That's what I'm asking.
Right. Yeah. It might be less universal, but I think there's still some degree of universality to it when the data set itself is large. Right. So that was mini lecture 0. Good. Okay. So extrapolating only need about 3 hours. Perfect. Okay. So to be clear, we propose that this connection is not merely quantitative or conceptual. If one wants a quantitative rather than merely qualitative framework in which to describe deep networks and calculate their properties to arbitrary precision, the correct theoretical tool is a certain kind of string theory. So if we want to use string theory as a quantitative tool to study machine learning, we can't possibly do that without specifically identifying what string theory we're talking about. I haven't specified it. So in the previous mini lecture, I told you the conclusion without telling you any details. Why did I do that? There's actually a number of reasons. I don't know the details, except in one simple case I'll be talking about. If I did, you wouldn't understand them. No offense, you guys are all very, very smart. I'll explain why you wouldn't understand them. Basically, it's because you're either too young or too old.
Some of us are in between.
It doesn't matter. It was discontinuous. No, there's a gap. There's a gap. Everyone is either too young, too old, or in the middle, you know literally nothing. I'll explain. But even if I knew, and even if you would understand, I might not want to tell you. So first of all, why am I even giving this talk on the relationship between string theory and deep learning if I don't know the answer to the key question of what string theory we're actually talking about? As I said, except in one case, which is not really in the regime of interest. The reason we can be confident in the conclusion is that it relies on two firmly established facts about machine learning, matrix ensembles, and string theory, which everyone in the field, except me, is either too young to know about or too old to know about the other one, or both. There's nobody in the regime of overlap. But we can use those two pillars as pillars of deduction to draw a conclusion even before understanding the string model correctly. So indeed, when we first started this journey, we had no examples that we understood. Now we have one, and predicting that we had this example was a prediction of this general line of reasoning. So the reason you wouldn't understand is that the connection between string theory and deep learning rests on these two ingredients, each of which individually is understood only by a tiny subsector of the theoretical physics community. Those two subsectors are basically entirely disjoint. In order for you to understand the logic, I will first have to describe each of the two pillars separately. So I'll do that in the remaining mini lectures. The two conceptual ingredients are that deep learning is realized as a particular kind of random matrix model with matrices of large rank n, and that large n random matrix models, without exception, have exactly equivalent dual descriptions as string theories. Yeah, so those are the two ingredients. But I'll mention just in passing, I mean, we're talking about, what's reason 3? Well, could it be dangerous? I mean, we're talking about basic research into fundamental mathematics and physics, right? What's the worst that could happen? And mini lecture. So basics of deep learning. Here's a basic overview. The simplest deep networks are what's called multi-layer perceptrons. The structure, sort of shown well up here, is an input layer, which is the data itself, and then a bunch of hidden layers, which you can have as many of as you like. And normally the width and the width is generally much larger than 3, than 5, and the depth, or much larger than 6, and the depth is generally much larger than 3. But it is what it is. Each layer is connected only to the two adjacent layers, the one above and the one below. And there's a critical distinction between linear and nonlinear multi-layer perceptrons. But what I want to emphasize here, which is almost never emphasized, but it should be because it's clearly important, is the importance of initialization, which is to say, before training, what is the ensemble of networks? Because many interesting phenomena show up even at that level. Before any of the nonlinearities are added, before training is done. So the devil is in the details, especially the stochastic initialization, which does not get talked a lot about, but which is kind of key for us, and is also key to this phenomenon, which clearly could not happen without stochastic initialization. So the structure of the network is described by so-called weights and biases. So the weights are a matrix, an n by n matrix, and the biases are an n component vector. And there's one at each layer, and they're independent at initialization. They're just chosen independently at each layer. And the weights and biases determine how the data is propagated from layer to layer. So in a linear perceptron, the propagation rule is just, an affine transformation from the previous layer. It's really boring. And then in a nonlinear multi-layer perceptron, you just apply a nonlinear function component-wise to each component of the hidden layer at each layer, okay, to each individual node. So these numbers which live at each node are called the so-called pre-activations, because this nonlinear function is sometimes called an activation function, but that's not going to be so important for us today. So the activation function is called the sigma. So I'm going to focus on for now on deep linear MLPs, and I'll set the biases to 0 also, which again you don't have to do, and you shouldn't do in practice, but I'm just talking about that because it's an excellent laboratory for our considerations. And as a string theorist, you should realize it shouldn't make too much difference because there are n squared degrees of freedom here, only n degrees of freedom here. So the weight matrices are where all the closed string dynamics lives. The bias vector is a kind of d-ring. Yeah.
Not sure I understand how could you have like a deep linear. Like, it's not. I think it's equivalent to having a single layer.
It is. Well, it's not. It's not equivalent to having a single layer. No, not
Because of the ensemble, just so that.
Yeah, because of the ensemble. But the ensemble is important. The ensemble is how you get this remarkable behavior, right? So I mean, the way I would say it is that any individual affine transformation, of course, can just be obtained with one layer, but the statistical favoring of some decompositions over others is really important. It's where you get this big overparameterization from. It's what empirically it's why you get good behavior for highly overparameterized networks.
So you don't think the nonlinearity is like relevant?
It is relevant. It's relevant for getting the critical point. So this is so you can still do it, and you have to do it to study what we really want to study. But so what's the right way to say it? It's like studying the renormalization group. You can see beta function like behavior in the linear MLP, but you won't see a fixed point.
Okay,
that's how I would describe it. And understanding the beta function like behavior is kind of the first step. But I mean, we know in principle how to put in the nonlinearities as well. There are various ways you can do it, but I'm not going to have time to get to that. Okay. But yeah, it is important. You can't get a fixed point without it, and that's one reason why people definitely want to put it in, because this optimal behavior you get in this extremely narrow range of aspect ratios, you only get with some nonlinearity. And when you turn the nonlinearity off, by the way, this is not something which the literature talks a lot about, but we understand how to do this in a controlled way. There's a sort of, I can't remember whether it's in the slides, but there's a controlled way of always turning the nonlinearity off, basically by making this activation function very broad, right? So you make it some random function, you take some random function, a sigma tilde of y, and then you define sigma of z as 1 over g times sigma tilde of gz, right? So as you take g to 0, the activation function gets infinitely broad and it becomes just the identity. And in that limit, the critical depth goes to infinity, right? So that's why you never get a critical aspect ratio when for a linear network. But you can kind of see in a controlled way where the critical aspect ratio goes. It's not mysterious. I mean, it's not in principle mysterious. Very good questions all so far. Next question, if any. Okay. Right, so but yeah, linear networks are a little bit boring. They're not that useful for practical problems because you don't get the fixed point. Yeah, you'll see a lot of important stuff. So the weights and biases at initialization prior to training are drawn independently from a Gaussian ensemble at each layer. And that that's what's important about what you asked, right? The number of there are, even in linear networks, there are things which you can construct in sort of many more ways for deep networks than others. And we're also going to assume that n is the largest, the width of the hidden layers is the largest parameter in the system, except possibly the depth, which can be taken comparable. And in particular, n will be parametrically bigger than the number of variables in either the input layer or the output layer, and much larger than the size of the data set. So now let's consider what sort of ensemble is defined by the network at initialization. So this ensemble is defined prior to training, so the data don't enter the ensemble at all. We just have an independent Gaussian distribution of weight matrices at each layer with no correlations in the matrices between layers. So this ensemble at each individual layer is well understood. In the large n limit, a Gaussian distribution of random matrices has eigenvalues that obey the famous Wigner distribution. So the parameters here, the maximal eigenvalue, the normalization constant, and n depend on n and the variance, and then deviations from the semicircle law are suppressed by powers of n and vanish as n goes to infinity. So at the level of each individual layer, the ensemble is boring, although that's essentially the ensemble I'm going to string theorize at the end. Despite this, surprisingly, even the network at initialization contains non-trivial, non-Gaussian phenomena, having to do exactly with the number of ways in which you can build certain affine transformations being much larger than others. That's where these non-Gaussian entities come from. So how is this possible? So I think the simplest way to explain it is in terms of what I'll call the actionization of observables. So even weakly coupled or strictly Gaussian theories can generate highly non-trivial, non-Gaussian correlation functions when one considers so-called large observables. And by large, I mean you consider an observable containing a very large number of insertions of the Gaussian random variable. So for a large enough number of insertions, the back reaction of the observables is large enough to drive correlations out of the Gaussian regime. So what's the criterion? So to understand it, you represent the observable, whatever observable you're looking at, as e to the minus log of the observable, right? So it's just a tautology. But if the observable is large enough such that the dominant saddle point of the combined action has a large action, then the expectation value of curly O will be badly approximated by a Gaussian action and well approximated by a non-Gaussian action. So if curly O contains enough insertions of the Gaussian random variables, then you'll need to actionize the observables to get a controlled perturbation theory.
But for this, don't you need an observable that's parametrically large?
Yeah.
Somehow.
Yeah, that's what I mean. But when I say it has to contain a large number of insertions, I mean literally, basically the number of insertions has to be 1 over h bar.
Yeah, that's okay.
Yeah. But so, I mean, this is a regime which comes up in various corners, and so it comes up in physics, but I don't know, I just made up the name actionization, but it comes up in lots of different places. The Zeno effect, semi-classicalization of scattering with highly multiparticle outstates, large order behavior perturbation theory, large quantum number limits, blah, 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 blah. It doesn't have a name. I'm just calling it actionization. So this is where the large depth becomes important. The individual weight matrices are each Gaussianly distributed, and the spectrum of the product of a fixed number of weight matrices can always be computed via simple weight contractions and a Gaussian ensemble with vanishing correlations in the large n limit. So the usual weight contraction thing. This is the reason why large but shallow networks tend to behave somewhat trivially. They are structured on linear transformations with a universal Gaussian structure, which doesn't allow much expressivity, which is the jargon deep learning people use for the range of functions it can access. So the typical functions one builds have a rather limited range of behaviors. But for deep networks, with the depth comparable to the width, the situation is different. And we can understand that difference in terms of what I'm calling actionization. So a paradigmatic observable one might compute, closely related to training, would be something along the lines of the secular determinant of the linear function that propagates data from the first to the last element. So, right, so the secular determinant of the product of so following this Roberts-Gaeta paradigm, we take the double-scaled large width limit, where the depth and the width of the network are taken large together. So a paradigmatic observable one might compute closely related to training, okay, would be this. So the behavior of this observable and its correlations with other observables is highly non-Gaussian. And in the double scaling limit, where L scales with N, there are L, which is order N matrices in the product. So the log is comparable to the sum of N terms, and that enhances the contribution to the action by a factor of O to the N. So that overcomes the 1/n suppression of non-Gaussian entities. And let me pause to note that this particular observable is the actual partition function of a trained neural network that's trained on a particularly idiotic question. So you can imagine a dystopian future where, students are really, don't know anything, they don't know how to compute anything or do anything on their own without using AI assistant, dystopian future in the far future, 2 or 3 years from now. Humans are not yet dumb enough and dependent enough on AI to need to train a deep network to solve the problem of multiplying a vector by a scalar, right? So you can imagine assigning this homework problem to your students in 2 or 3 years, and they'll have to use AI to solve it. They'll have to feed that into a deep network because nobody will know how to do anything anymore. And they will have to now have a network trained to solve this problem. And if you literally train a network to solve the problem of multiplying a vector by a scalar, the loss is literally this observable. It's literally this log of the secular determinant of product of weight matrices minus lambda. So we aren't quite at the point where we now need to train a network to do this, but someday we will be at that point. And so this is not an academic question. So these large non-Gaussian entities appear as a known phenomenon, even in linear MLPs in the double scaling limit. So Robertson-Gaeta's review gives a nice calculation. It's a very lengthy multi-chapter calculation of these non-Gaussian entities for these correlations among the pre-activations as they propagate from layer to layer. The simplest to compute, even though the higher point non-Gaussian entities behave the same way, is G4 minus G2 squared, right? The quartic correlator minus the free part, Gaussian part normalized by the Gaussian part. So we know that at large n and fixed depth, this will always go to 0 as a power of n, but in the double scaling limit it doesn't. It has actually an exponential growth with n. So that's essentially why you never get a fixed point, because this is an exact expression for the linear MLP in the double scaling limit, right? The non-Gaussian entities just actually grow and grow. They don't saturate. There's no unitarity bound. This is a non-unitary system. They can just do whatever. With nonlinear activation functions, you can get the non-Gaussian entities to stabilize empirically. We don't know yet.
I have a question about that, because I think part of the magic that we see in the networks is also that the training data is highly structured, and this is solving an unstructured problem.
Well,
so how do you reconcile that?
I would say that the existence of large non-Gaussian entities is a necessary condition for interesting behavior. Yeah, not sufficient. Yeah,
Makes sense.
I don't know what's known. I don't know what's known if you sort of average over random data sets.
Yeah.
What's known about that? I don't know the answer to that. But I think you definitely won't get any you wouldn't get any interesting behavior at all if you couldn't get non-Gaussian entities.
That makes sense.
And that's why people wanted to take this kind of limit in the first place.
So in that case, for this problem, the nonlinearities would probably act as more like a cutoff, right?
Well, but because it's exactly right. If there were nonlinearity, yeah, but there were, right. If there were nonlinearities, I actually don't know if it gives you an automatic cutoff. I think we had some confusion over how many tunings there are because at first we wanted to just guess what was the universality class of the string theory of the string theory you get in the end. And one way to do that is by counting the number of tunings. But there's something weirdly ambiguous about the number of tunings in this setup, which this is somewhat technical. Let me not get into it. But to some extent, you have to tune. It's not just an automatic self-cutting off thing, even once you introduce nonlinearities. There's a sort of basin of attraction sometimes, and then sometimes there isn't, and sometimes you have to actually tune to get to it. And that was kind of confusing. So, yeah. Okay. Yeah, so for the linear MLP, the network is integrable, which is why they could, compute these non-Gaussian entities exactly and show that they get big. So the linear MLP can serve as a nice benchmark for the string dual, even though, of course, you do have to introduce nonlinearities to get anything really useful. Okay. So mini lecture 3, I can probably go through somewhat quickly because people here are, a lot of them are string theorists, but so at least you've sort of heard of this stuff. So, there's this old subject called matrix string duality, of which the modern incarnation is ADS-CFT. On one side, we have double-scaled large N matrix models. On the other side, we have non-critical string theory, low central charge CFTs coupled to Liouville theory. The duality is that these describe the same physics. And so there are many people who contributed to this in this early part of the story. And of course, it was taken over by ADS-CFT. But okay, so you've all heard about this large N string gauge theories of string theories thing. One uses double line notation to classify Feynman diagrams by topology and so forth, and one gets a planar expansion of the partition function of any observable. So right, so genus 0, which scales as n squared, are planar diagrams. Genus 1 is the torus, scales into the 0. Genus 2 and higher scale as negative powers of n. And even very simple gauged matrix models show this structure. So yeah, I'm not gonna, maybe in view of time, I'm gonna skip over some of this older string matrix stuff that we can come back to it. This is what sort of inspired us. But let me talk just a bit about the actual example we understand, which is a bit more sort of modern than this old string theory, old matrix string stuff. So I'm going to talk about the ensemble defining the one-layer Rosenblatt perceptron. And just to be clear, the wave matrices at initialization are real. They're real, but without any particular symmetry. So W is not equal to W transpose, but it is equal to W star. So it's not a Hermitian matrix model. It's a non-Hermitian matrix model. So the basic problem, which was not solved in the literature, is what is the string theory that describes the large N expansion of this gauged matrix model? So there's an ON symmetry. There's, if you like, one symmetric and one anti-symmetric matrix, matrix. and a Gaussian potential. Gaussian single trace potential. So the description of it is in terms of what's called Digraph-Vava duality. So to explain it, I'm going to start with ordinary Digraph-Vava duality. Wait a second. So the basics, the basic Digraph-Vava duality is a duality between a Hermitian matrix, a Hermitian one matrix integral on the one hand, a Gaussian Hermitian one matrix integral on the other, on one hand, and the so-called topological B model, the closed-oriented B model, on the deformed conifold on the other side, on the string side. So the deformed conifold is described by this geometry. So it's an affine subvariety of 4 complex dimensional affine space. It's just a quadratic, the most generic possible quadratic subvariety. There's an SO4 symmetry, which is not so essential right now, but it's useful as one goes on. And this duality is very well understood. It's been generalized in many ways, but it was not generalized yet to the thing one needs to generalize to describe these ensembles defining networks of initialization. So we're going to generalize in 2 ways. We generalize by taking what's called the Ferrari geometry, the 2 matrix model, and then we orientifold in a specific way that changes UN to ON and makes one of the matrices symmetric and one antisymmetric. So this variant was not studied before, apparently, and so we found it. So in the remaining 4 minutes, I'm going to give the basic intuition behind Digraph-Vava, explain how we modified it to get this real Ginib. Nobody could actually tell us how this was pronounced. So the basic intuition, one sort of intuits these dualities the same way that ADS-CFT was intuited, which is to say you start with some branes wrapping some cycle and some geometry, and you start by not taking the back reaction into account in order to just get the weakly coupled Lagrangian, and then as you go to strong coupling, you have to take the back reaction into account, and you describe the large N dual by the back reacted geometry, just like in ADS, just like D3 branes in flat space give you ADS5 cross S5. In the same way, what's called B branes wrapping a CP1 in the topological in the deformed resolved conifold in the topological B model. The back reaction blows down the CP1 base. A 3 cycle is blown up, and the branes disappear and turn into some sort of mystical flux, which is not well understood in the B model itself, but the duality is very well understood. So understanding the orientifolding at that level allows you to follow it through to the duality. So yeah, let me start with a remedial review of Joe Polchinski's legacy, which is branes and orientifolds. So some basics on branes and O planes. The DP brane has a P+1 dimensional world volume in full superstring theory. The codimension is 9 minus P. And in topological string theory, when I say D5, a D5 in full type 2B corresponds to a 2 complex dimensional variety, because there are 3 kind of invisible directions. An explicit description of the pre-back reacted geometry is as follows. In topological string theory, in the topological B model, one has this so-called resolved conifold, which can be thought of as curly O minus 1 plus curly O minus 1 over CP1. So it's a complex three-dimensional variety. The easiest way to describe the resolved geometry is to use projective coordinates. So there are two base directions. This is the CP1. There are two fiber directions, and the homogeneous redundancy acts on the p's exactly opposite as it acts on the capital Z's. So the products, these four independent products, are gauge invariant. But these satisfy an algebraic relation. They satisfy Zm equals 0. And then in the deformed conifold, that gets deformed to Zm equals mu. So now how do orientifolds work in this setup? Say you have an OP plane and that n p-branes are parallel to that. So that's the simplest case, that's the basic case, which we use as a reference point. The UN gauge group turns into an ON gauge group. The transverse scalars moving the branes away from the O plane are in the adjoint representation. So in full superstring theory, if it's a DP brane in an OP plane, then we have, exactly this. We have ON instead of UN and all anti-symmetric representations for the transverse scalars. You have 9 minus p transverse coordinates on each brane, x transverse is an adjoint of SON. It's an anti-symmetric tensor. Sorry, it's using the wrong version of the slides. Sorry, I'm using some old version. I'm sorry, guys. Okay, it's okay. I'm just gonna describe it verbally. Anything I left out. X parallel is longitudinal to the O. Okay, sorry. You could also consider an OQ plane which contains all the directions of the branes, but has more directions than the ones that are longitudinal to the branes. So let's say you have k extra transverse directions. All the world volume directions of the DPs are parallel to the OQs, but the O plane has some other directions as well. So branes have x transverse and x longitudinal, where both are transverse to the DPs. X longitudinal is longitudinal to the OQs, and X transverse is transverse to the OQs. And in this setup, X transverse is an adjoint, an anti-symmetric tensor, and X longitudinal is a symmetric tensor of O. So the moral is that if you want to make a matrix from anti-symmetric to symmetric, and it can be thought of as a transverse motion of ND branes, just change the O projection by a symmetry under which that direction is odd. Okay. So this is the Ferrari model. For general U potentials U and V, the geometry is this. So little u and little v have nothing to do with big U and big V. Sorry, other than being the next letters in the alphabet before U and X. So this is the deformed geometry of the deformed conifold, and it represents a two matrix model, which is Gaussian with a deformation. But the deformation is trace minus xy plus trace u of x. I think of v of x or v of x plus trace w of y u of y. But for the case we're considering right now, we'll just take big U and big V to be 0. And so we just get back the same geometry, the deformed conifold. The only difference is going to be the orientifolding. We want the O5 wrapped in the same place, which is to say we want an involution whose fixed locus contains, sorry, if we want to consider the warm-up for an involution, which is just the base, we take in the pre-back reactive description, we just reverse the directions of the fiber coordinates, and then we get in affine coordinates something which reverses all four of the affine coordinates because they are equal to the product of P and Z. So all four of these reverse. But since Z squared equals mu, there's no fixed point under this geometry in the back reacted. There's no fixed point under this involution in the back reacted geometry. The simple orientifold of Digraph-Vafa, not of the Ferrari model, but of just Digraph-Vafa, gives you a symmetric ensemble with ON symmetry and then anti-symmetric matrices, and it's just this fixed point free orientifold of the deformed conifold. Then we change this up a bit. If we want this two matrix model where W is equal to W transpose, then we just need to change the orientifold action in a simple way. We want X plus Y to be, this should be plus, excuse me. We want X plus Y to be even and X minus Y to be odd, so that Y will be X transpose. So in other words, we just modify the orientifold projection in the simple Digraph-Vafa by an extra transformation which reverses X and Y, and we get a Gaussian ensemble of a non-symmetric matrix, of a real non-symmetric matrix where the action is trace X transpose. So you've now seen the following. Large networks of initialization can be understood as a large number of purely Gaussian matrix ensembles. This is dual to L decoupled copies of a particular non-unitary string theory. Training the network corresponds to the insertion of large complicated observables into the ensemble, coupling the various ensembles in a nearest neighbor way. This corresponds to deforming the world sheet action of the string theory in a way that couples disjoint universes or disjoint layers. In the double scaling limit, these universes form a continuum approximating a continuous time in string theory. We don't know yet what the string world sheet theory becomes after deformation by training, but in general grounds, it remains a string theory with some world sheet action. And whatever the world sheet action is, it's dual to some sort of possibly non-unitary matrix quantum mechanics. In the case of the linear MLP, it's a one matrix quantum mechanics. Such models are generally integrable. As a benchmark, one should compute the non-Gaussianities in linear MLP using the integrability of the string theory. For one layer, we have an explicit form of the world sheet theory for the ensemble of networks of initialization. So thank you. I'll end.
Do you have any ideas about describing the opposite limit?
Which opposite limit?
So one where the width is finite, but it's infinitely deep.
Oh, good question. Yeah, that's a great question. I don't know the answer to that. Well, no, I think it's very strongly coupled. It would be more strongly coupled than a double scaled string theory than a double scaled matrix theory. So it would probably be something like M theory or whatever, right? It would not be something with weak string coupling, right? So it's an interesting empirical fact that the regime where the behavior is good is the behavior where string theory is applicable, right? So it's not just one of these examples of like, oh, like here's some random system, I want to make it a string theory. Like it's not like that, right? It's the system is really telling you that it is a matrix ensemble. The ensemble quality is important, and the behavior is interesting in a double scale. In an element where the theory is double scaled in the usual string theoretic sense. So string theory really seems to have something to do, or seems very well optimized to this this limit where all this interesting behavior is happening. I would just say that when we got started, we got started with the problem as I described it in the introduction, without any preconception that string theory was the relevant tool. Like, it was an output of our considerations that it seems to be in that regime.
But maybe I didn't understand what was the upshot of what you said.
Yeah.
Because you were still studying like very wide, but one layer.
Oh, just for purposes of concreteness.
Really writes them down. But you think like as you write down more layers, I mean, you're going to have more flavors of these matrices around, right? So it's going to become a more complicated construction if you want to think of it geometrically or something like that. And you want to be in a regime where that complexity is actually scaling at the same time as the width.
Yeah.
So it's not obvious to me that that's still a string theory.
Oh wait, sorry. No, I don't think it is a string theory. No, wait, sorry. You mean when
it's a non-zero Q, right?
Oh, but non-zero but fixed Q.
Yeah.
Yeah, but from the ensemble point of view, you can see that that's the limit which it does correspond to double scaling. In other words, you have a loop enhancing parameter and a loop suppressing parameter. And the loop enhancing parameter is really the depth, right? The fluctuations really do grow with L and fixed N. You need large N to suppress them. So it behaves in really the same way as G squared. G squared N controls string theory. L is basically plays the role of 1 over G squared. That's why it looks.
Thanks.
Yes. From an engineering point of view, what would you like to understand? Like, how do you make these things more efficient? Like, I guess, for example, in that graph, you would like to make it go down as fast as possible, so that the loss.
For instance,
is that something that the string theory could help in some way?
I think so, yeah, and I think it can do even more basic things that. I mean, there are many basic things which are only, even though this is a very sort of coherent picture empirically, it has very little, theoretical understanding of it, quantitative theoretical understanding. For instance, finite width corrections are something that people really would like to know how to compute in order to make, to not have to make large networks so large. Right? It's nice to be able to make them not so large if you can. And nobody has any principled understanding of how to compute finite width corrections. So, the equivalent of the RP2 or the torus is something which people don't know how to compute from first principles for nonlinear MLPs. Things like, as you say, optimizing the parameters, optimizing the training algorithm, all sorts of things. More ambitiously, there's this thing called the lottery ticket problem, which tells you what that means. What AI people, when they refer to it, what they mean is that as the network gets larger and larger, a smaller and smaller fraction of the network actually does anything useful. So the network is parametrically dominated by junk at large N. So when the network gets very large, finding the piece of the network that actually does something useful is like winning the lottery. That's why they call it the lottery ticket problem. We have a theory or some sort of idea for how you can solve the lottery ticket problem. Essentially, it's expected that the largest eigenvalues of the weight matrices should be the most important when the network is large. And in string theory, at least for simple things like C equals 0 or C equals 1, we understand well enough how to geometrize the eigenvalues into a Liouville direction that we understand where the important eigenvalues live. They live, basically at the Liouville wall. That's a slight simplification, but there's a functional understanding of how to geometrize the most important eigenvalues. So, of course, we don't know what the right string theory is in this interesting limit yet, but we have a kind of recipe to get us there. So hopefully, at some point, we will understand it in those terms. And there's even for simple digraph, there is some understanding of a scaling limit where you focus in on the the edge of the semicircle, right? The corner of the semicircle where the eigenvalue distribution goes to zero. There's some sort of scaling limit you can take, and it gives you a thing called topological gravity in 2 dimensions. Pure topological gravity, the so-called Witten-Kontsevich model. So there should be some analogous double scaling limit to multi-layer networks, where you should be able to understand the important parts of understand and isolate the important parts of the network into some kind of legal-like theory. But yeah, we don't have that at present.
All right, let's thank Simeon for a stimulating talk.